Okay, so this is the first example problem from lecture 4.3, which I had solved during that lecture using tau equals I alpha and F equals ma, Newton's second law. Now I'm going to resolve it using energy methods, and we'll see maybe if this is any easier or not. Okay, so we've got this 10 Newton weight that is initially at rest attached to the drum that's initially at rest. The weight, when it's released, is going to fall down. That's going to cause the drum to rotate in a clockwise direction. And so the question it really is, or one of the questions is, what is the angular acceleration of the drum after it's let go and it falls from rest? So I'm going to set up this for energy. I'm going to draw my system at two states. So first I'm going to draw it in the initial state. So here's the drum with the rope and the 10 Newton weight. There's 10 newtons being applied here. And I'm going to call this state 1. And I can say a few things about state 1. The angular velocity at state 1 is 0 because this is all at rest. The velocity v of the weight is also 0 at rest. I'm going to say also that theta 1 is 0. So if we somehow measure the angular position of this drum, I'm going to say that's 0 at state 1. Now at some later time, which I'm going to call state 2, this weight will have fallen some distance farther down, still with the 10 Newton weight being applied to it. Now there are also some pin forces, OX and OY. That's X, that's Y. Same thing over here. There are pin forces, OY, OX. Okay, so at state 2, I'm not going to know omega 2. That's something I can solve for. And then if I know omega 1 and I know omega 2, then I can potentially solve for the acceleration, the alpha that I'm looking for. V2 I don't know, but I know it's related to omega 2. It has to equal R times omega 2 because the rotation of the drum and the vertical motion of the 10 Newton weight are connected by the rope, and so I can make that relationship. Theta 2, I'm just going to make this up. I'm going to arbitrarily say this weight has fallen and this drum has rotated one full revolution. So I'm now choosing arbitrarily that theta 2 equals 2 pi radians. So this defines my state 2. And I'm also going to pick a datum. Here, the position of the weight after it's fallen is my datum, and so I can say H2 is 0 because that's my datum. And now that I've chosen a datum, I can now say something about H1. And it's really just going to be the circumference of the circle, how much rope is let out as this drum rotates once. So this is going to be 2 pi r is going to be H1. Okay, so I think that's all the information that I can say about the two states. Now I can set up a conservation of energy equation. There's no friction involved here in the system, or there's no friction that does work. So I can set up a conservation of energy equation. So I can say K1 plus U1 equals K2 plus U2. So the kinetic energies, there's going to be a angular or a rotational kinetic energy for the drum and a translational kinetic energy for the weight. So I'm going to write those terms. I can have a 1/2 m, this is the mass of the weight, v1 squared, so that's the velocity of the weight, and then my angular or rotational kinetic energy is 1/2 I of the drum times omega 1 squared. That's the omega of the drum. So that's my total kinetic energy at the beginning. And then I have a potential energy, and the only potential energy here is the potential energy of the weight And so that's going to be mgh1. So that's my potential energy and kinetic energy at state 1, which is at rest. And then I'm going to have similar terms for state 2, 1/2 mass of the weight times the velocity of 2 squared plus 1/2 I of the drum omega 2 squared plus mg h2. And I know some things here. I know some things are 0. V1 is 0 because it's at rest initially. Omega 1 is 0 for the same reason. And h2 is 0 because that's where I picked my datum. So if we look at this, the only thing that I don't know, only quantities I don't know in this equation are V2 and omega 2, but I know those are related by this relationship up here. V2 has to equal R times omega 2. They're related through the action of the rope. So I have one equation and only one unknown, so I can solve this once I make that substitution that V2 is R times omega 2. So I can kind of rearrange this. Well, on the right-hand side, I have mg h1. On the right side, I'm going to have 1/2 times the mass of the weight. And now I'm going to express V2 squared as R squared times omega 2 squared. And then I've got 1/2 ID omega 2 squared. And I'm just going to collect terms on the right-hand side. So I have mg h1 equals 1/2 times the mass of the weight times R squared plus ID times omega 2 squared. I can solve this for omega 2 squared. Omega 2 squared then is going to look like mg h1 times 2 divided by the mass of the weight times R squared plus ID. And if I plug in what I know here, the mass of the weight, or the weight, mg, is 10 newtons. So that's mg. h1 is 2 pi r. R is 0.2 meters. And then I have the 2. Dividing that by the mass of the weight, which, if you look back at lecture 4.3 in the notes, I said the mass of the 10 Newton weight was 1.02 kilograms. Multiply that by R squared, which is 0.2 meters squared. Add to that the rotation, the mass moment of inertia of the drum, which we said in lecture 4.3 was 0.641 kilogram meters squared. So when I work all that out, I get an omega 2 squared of 39.209 radians squared per second squared, or an omega 2, if I take the square root, of 6.262 radians per second. All right, so I now know when that weight has fallen a distance of 2 pi r, what my angular velocity is, what my omega 2 is. And if I know omega 1 and I know omega 2, I can use now kinematics to figure out what alpha would be. And I'll do that on the next slide. And I can use this equation that omega 2 squared minus omega 1 squared equals 2 alpha times theta 2 minus theta 1. And I had said that omega 1 is 0 because it started at rest, and I had arbitrarily stated that theta 1 was 0. We needed some starting point, and theta 2 was 2 pi. So now I can solve this for alpha. Alpha is going to look like omega 2 squared divided by 2 times theta 2. And I just calculated omega 2 squared. I said it was 39.209 radians squared per second squared. Divide that by 2, and then my theta 2, which was 2 pi radians. And I get an answer of 3.12 radians per second squared, which is the same value that I got in lecture 4.3 when I worked this problem by F equals ma and tau equals I alpha. I don't know a direction. When I did it in 4.3, alpha came out as negative. Now, when I'm using energy methods, I don't get a sign that tells me the direction, so I need to deduce this myself. And just looking at the problem, you can see that as the weight moves down, right, as the weight moves down, this drum has to rotate in a clockwise direction. So I'm now going to say that alpha is 3.12 radians per second in a clockwise direction. And that's my answer for alpha. If I want to figure out my pin forces, which was the problem also asked for, OX and OY, I'm still going to have to sum my forces. Still going to have to use Newton's second law to figure out those. I'm not going to do that now because that would be the same as from lecture 4.3. I just wanted to show that I could determine alpha, the angular acceleration of this drum for this system, by using an energy method. It's up to you to decide whether that's easier than the tau equals I alpha method. Maybe it is because we didn't have simultaneous equations to solve. We just had one equation to solve for omega 2, and then we had to use kinematics. And use our kinematics to get the alpha.